Okay, this is going to be the day 2 video for AP Statistics Chapter 18 on sampling distributions. And yesterday in the day 1 video, we introduced the idea of the 3 levels, the population and the sample and the sampling distribution model. And then we explored the sampling distribution model shapes and standard deviation formula for the case where we have a numerical variable where we can calculate a mean. Okay. Today, we're going to investigate the same thing, but we're going to do categorical data. What if we had categorical data, some sort of data where we just had a yes or no situation? And so the only thing numerical we can calculate is a percentage, which we'll typically call a proportion in this part of the class of yes. So it's going to be a percentage of yes in a population. So for example, it could be something like where we have people, there's lots of stuff we can measure about people, but maybe we want to measure, do they have brown hair, right? They either have brown hair or they don't have brown hair, right? So that's a category, right? It's not numerical. It's not what percentage of it's brown or something like that. It's just yes, brown, or no, not brown, right? So if we have a yes or no kind of categorical variable, we can only measure the percentage of the population that's yes or the percentage of the sample that's yes. All right. So we're going to do the same kind of thing. This time we're going to go to the Mr. Felling site, but we're going to go mrfelling.com/SA2. SA2 stands for Statistics Activity 2. Okay. So if we do that, then we're going to get a little bit different looking screen. We're going to be asked about just the percentage in the population that is yes. So let's say we're talking about hair color and we want to talk about the percentage of people who have brown hair color. So let's make an assumption that in the population, 60% of the people have brown hair. Okay, so we're going to put that in as a proportion, 0.6. Okay, and then let's set our sample size to 16. Okay, as a start, and we'll click sample. Okay, this is set up to do things a little bit differently. It's got a section of the population here at the top that's marked in blue for yes, and then in gold for no. And so my statistic, or my parameter up here would be the percentage of the population that's brown haired, and so we set that to 0.6. Okay, so this is the one exception to the Greek letter regular letter rule. If we did this properly, in fact, let me go to the notes for a second and show you. If we did this properly, we would call this pi, this proportion pi, using a Greek letter, and we would use p down here for sample. Okay, and in fact, in calculus-based statistics classes in college, they usually do this. They use pi for the population and they use p for the sample to keep with the idea that we use Greek letters up here and regular letters down here. But that's so confusing because pi means the constant 3.14. We break our rules and instead we use p up here and we use p hat down here to indicate the sample, which is also confusing because we know p hat is the predicted y value, right, for an LSRL. But that's the convention for AP statistics and all non-calculus statistics classes. So our P is the population percentage of brown-haired people, and our P hat is the percentage in the sample. So in my case here that I'm running a line, right, 60% of the population has brown hair. But in our sample of 16 people, I had 0.56, so 56.3%. And of course, when you ran this, if you ran this with me, you got a different thing, right? And just like before, we have the population level, the sample level, and then down here we have the sampling distribution level. So what this is down here is a p hat. This little dot, which I made purple this time, represents a p hat value, okay? And if I were to take another sample, I'm going to get another p hat value, right? So what you can do is press the sample button and then see that it takes a different sample of people. And in this case, I got a kind of a crazy low value. Only 25% in this sample had brown hair. And so I have a p hat value down here. And if I press sample again, okay, this one was back up here around 56%. I'll do this again. This time I got one with an unusually large number of brown-haired people, 75%, so p hat here. So you can do that over and over and over again. And then eventually, if you want to try them a bunch, let's do 400 samples, each with 16 people, and we're finding the percentage that have brown hair. So if you click the sample 400 button, you'll get this. Now, this looks a little different. Notice it looks like the shape of it is kind of normally shaped, but it's not filled in. That's because this is really a binomial situation, and this is binomial PDF for a bunch of different cases here, like this. Okay, but it does form a shape that looks normal. So let's talk about that a little bit more in the notes, right? This has, even though this is not a numerical variable, it's a yes or no variable. Once I find a percentage, right, that percentage is numerical, right? This is a number, 0.688. And so this distribution is numerical down here. So it has a shape, it has a mean that we call the mean of the p hat values, and it has a standard deviation that we call the standard deviation of the p hat values. So these are the symbols for the sampling distribution of sample proportions. Yesterday we talked about sampling distribution of sample means. Now we're doing sampling distribution of sample proportions. All right. All right. So then the reason why this has the appearance of a line is that this is really a binomial distribution. If we had 16 people in our sample and we wanted to know what percentage yes they had brown hair, then the probability of 0 would be binomial PDF out of 16, 60% chance of having brown hair, 0. And the 1 for 1 would be the same thing with the 1, and then the 1 for 2 would be the same thing with the 2, all the way up to this one would be the same thing with a 16. Okay, and if you plot that all out, it has a certain shape. And we know that binomial distributions, they can be either skewed or they can be symmetrical depending on how close p is to 0.5. This 0.6 here is pretty close to 0.5, so we have something that's pretty symmetrical and looks almost normal. Okay. All right, so this envelope is basically the normal approximation to this binomial model. Okay. All right. So it turns out there is a formula for computing the standard deviation and the mean. It's a little harder to try to get it experimentally like we did yesterday, so I'm just going to show you algebraic where it comes from. Because this is binomial, then we know that it could be approximated with a normal approximation if the sample size was big enough. And if that were true, then the mean would be NP and the standard deviation would be the square root of NPQ. Okay, but because we're talking about a proportion, which is a percentage, we have to take that number and divide it again by the number, right? So if I take NP and I divide it by N, then I'm finding the fraction of people who have brown hair. This is the expected number of people who have brown hair. Divided by N gives me the percentage. The N's cancel and it's P. And that's the reason why the center of this envelope here is centered right here at close to 0.6. Because if 60% of the people have that, that's the expected value. So if I just divide that by 16, then that means 60% should be the center of this distribution. Okay, so the formula for the mean of the sampling distribution for p hats is the population percentage of yes. Okay, and for the standard deviation, if you take the square root of NPQ and you divide that by n, that's the same as dividing by the square root of n squared. And so if we put that inside the fraction, this n gets canceled by one of the n's, and we end up with the square root of PQ over n. So that's the formula, right? So we have formulas here that the mean of this envelope over here, this mean, will always align itself with whatever the population proportion is of yeses. And the standard deviation here, the standard deviation of the p hats, that's going to be equal to the square root of PQ over n. Okay. All right. Right, so what we can do really, if you want to play around with this, you don't have to do this, is just verify that this is true. So I left some things in your required practice packet so you could practice with some things. Like in this case, we had a sample size of 16. So if I were to and p was 0.6, I should expect that this mean should be 0.6, and in this case it was 0.601. In my case over here it was 0.599, and I'm sure if you ran this it was really close, the mean down here, right? But what about the standard deviation? So the square root of PQ over n, well, if p is 0.6 and q is the other 40%, if you took the square root of 0.6 times 0.4 divided by the sample size of 16, we should have a standard deviation of the sampling distribution model of about 0.122. And when I ran that before, I got 0.123. When I ran it just now, I got 0.127. So yours should be very similar. Okay. And so I do have a little section here in the notes where you could try this. You can try resetting and trying different P and N values. Okay. So let me just go through the steps here. And if you want, you can pause and you can just go through the steps that are in the in your sheet. But I'm just going to continue on in the video here, assuming that you've paused and tried it yourself if you care to. Let's try P is 0.2 and N is 4. Okay, so if I were to do that, reset and set the probability to be much lower, which should give me a skewed value, and then 4. Then what do I get for my shape here if I do 400 at a time? I can't really see this till I do 400 at a time. Right. So sure enough, everything's happening more down here at the 2%, but because I only had 4, I have fewer lines. This is much more sparse. And this binomial distribution is no longer approximately normal, right? It's very much skewed right, just like we would expect for any binomial, right? But what happens as the sample size increases? If I increase the sample size, let's go from 4 up to, let's say, 16. Even though P is low, if I do 400 of them at a time, then I'm going to get a lot more lines. And sure enough, this is much closer to being normal. Not quite. There's still a little bit of skew, more tail over here than over here. But if I were to go up to, say, 50, something like that, then I have, when I do a whole bunch of trials, a whole bunch of lines, right? And this is starting to look very much like a normal distribution, just a tiniest bit of asymmetry there, right? All right. On the other hand, let's say that let's see what the notes is going to suggest next here. Let's say that I tried different sample sizes with, let's use a small sample size like n, but let's try different p-values. So let's use 6 for the sample size, and I'll start out with 0.2 for the proportion of yeses. So that's going to turn out to be pretty skewed, right? Quite skewed, not normal. But if I keep the sample size low, but I increase P to closer to 0.5, what happens? So if I go up here to, say, 0.5, we put it right at 0.5, and then look at a whole bunch, then the sampling distribution is back to being approximately normal, just because anytime I have a binomial where P is close to 0.5, no matter how low the sample size is, this is approximately normal. So all those rules that we learned in probability about when can you approximate a binomial with a normal, they apply here too. Whenever that is met, when P is close to 0.5, or even if P isn't 0.5, but N is large enough, then you can say that the shape is approximately normal. All right, so let me just pull all those kind of experiments together here, and we'll summarize a couple things, right? If you recall from before, as long as NP and NQ were at least 10, then you'd have an approximately normal shape, right? That's called the success failure criteria, right? And that turns out to be the same thing here, right? When we had means yesterday, we said that the central limit theorem says if the sample size is at least 30, then the shape will be normal no matter what the population shape is. And we can even have n less than 30 if you're sampling from something that's approximately normal. Okay. Now we're saying for the yes-no categorical case, where we're talking about proportions instead of means, then for us to have a nearly normal approximation, NP and NQ have to be at least 10 so that the normal approximation applies. And then the other thing is that we have slightly different formulas, right? The mean of the means matches the population mean. The mean of the proportions matches the population proportion. But when it comes to the standard deviation, we have that the standard deviation of means is the standard deviation of the population divided by the square root of n. But for proportions, the standard deviation does not depend upon the standard deviation of the population. It depends upon the center value, p. It's p times 1 minus p over n. So this is where the big difference is. And that's going to turn out to have other ramifications later that we're going to explore in chapters 23 through 25. All right. All right, so that's all we're going to do in the second part. At this point, we're still not at the point where we can really do anything in the practice packet yet. So you don't need to do anything until we get through the third day. But this is the second day video.